Hello students, today we are going to move on with our vector calculus. In fact, we're going to focus on calculus on vector valued functions. So our objective today is to be able to just analyze and sketch a plane curve that's given by a vector valued function, extend our concepts of limit and continuity to vector valued functions, and of course differentiate and integrate vector valued functions. So a plane curve is defined by a set of ordered pairs f of t, g of t. Well, x would be f of t and the y coordinate would be g of t. So we've seen how we can do that when we've talked about parametric equations with the parameter of t on some interval I. Another way we could represent this curve is by using a vector valued function. This type of function maps real numbers to the vectors and is the form. Notice that that's a bold R, so that's our vector valued function, and it has an x component, that's v of, or f of t, and a y component, that's g of t. These are component functions. Technically, a curve consists of a collection of points and is defined by a parametric equation, so two different curves can have the same graph. For example, r of t, where it's given by the vector valued function where the x coordinate is sine t and then the y part is cosine t, and r of t where the x component is sine of t squared and cosine of t squared, has a unit circle as its graph, but these equations do not represent the same curve because the circle is traced about in different ways on the graphs. So be sure that you see the distinction between a vector valued function r and a real valued function f and g. All of the functions of the real variable t, but r of t is a vector where f of t and g of t are real numbers. So there's a difference. One's basically dealing with numbers, or numbers, and the one's dealing with functions. Vector valued functions serve as a dual role in the representation of curves. By letting the parameter t represent time, we can use vector valued functions to represent motion along the curve, part of the motion. In more general case, you can use vector valued functions to trace the graph of a curve. In either case, the terminal point of the position of the vector r of t coincides with the point xy on the curve and is given by the parametric equation. So here we can see that we've got a curve, the dark curve, and we have the value of the vector valued function for r of t0, t1, and t3, or sorry, t2. The arrowhead of the curve indicates the curve's orientation by pointing to the direction of the increasing values of t. So as time increases, that would be the curve. Unless stated otherwise, the domain of a vector valued function r is considered to be the intersection of the domain of the component functions of f and g. For instance, the domain r of t equals the vector valued function ln of t square root of 1 minus t is the interval from 0, not including 0, up to 1. In other words, it has to satisfy those two guys, the intersection of the domain of those two curves. So the domain of the natural logarithm, in fact, let me write that on here. The domain for the natural logarithm is 0 to infinity. But then the domain of this curve here, so if we were to think about this graphically here, so if it's 1, it's 0. So this guy's going to start from here. Oops. Let me do this in a different color here. So here's 1, but if t gets bigger than 1, it's undefined. So this curve actually goes in this direction. Sorry, I'm having some technology issues here. Get this going. There we go. So that's what we're going to get. Yeah, it's good. And so if we take the intersection of these two curves, so this first or the second curve here is going to have a domain of negative infinity up to and including 1. So the intersection of those two things is 0 to 1 inclusive. So let's go ahead and try to sketch the plane curve represented by the vector value function r of t equals the vector valued function 2 cosine t comma negative 3 sine t. And we're going to go from 0 to 2 pi for the value of t. So from the position of the vector r of t, you can write the parametric equation. So you've got x is going to be equal to 2 cosine t, and y is going to be equal to negative 3 sine t. Solving for cosine t and sine t using the identity cosine squared t plus sine squared t equals 1 produces the rectangular equation x squared over 2 squared plus y squared over 3 squared equals 1. The graph of this rectangular equation is an ellipse and is shown here. So here's our ellipse. So this would be the graph of this particular vector valued function. The curve has a clockwise orientation. In other words, it's going to turn in this direction as we start from 0 over here. That is that t increases from 0 to 2 pi. The position of the vector r of t moves clockwise, and it's going to form an ellipse. Okay, limits and continuity. So our definition of a limit of a vector valued function, if r is a vector valued function, the form r of t equals the vector f of t g of t, then the limit of r of t as t goes to a is simply the limit of f of t as t goes to a and is g of t as t goes to a. So if r of t approaches the vector L as t goes to a, then the length of the vector r of t minus L will approach 0. So it's basically the same definition. It's just written in the context of a vector valued function. So we want that limit to go to the difference between these two things to go to 0. The following definition can extend to the notion of continuity. So the definition of continuity on a vector valued function. A vector valued function r is continuous at a point given that t is equal to a when there exists r of t, that's the vector valued function, exists as t goes to a. In other words, the limit of the vector valued function as t goes to a is equal to the actual value of the function, vector value function at a. So let's look at an example of that. So r of t is given by t comma the square root of t plus 1. So let's find the limit as t goes to negative 1. And also let's determine if it is continuous. So let's go ahead and do A. So we want to find the limit as t goes to negative 1. So what is the limit of that? Well, let's see here. That is a continuous function. So if I just plug negative 1 in there, that's going to work. And so we just go ahead and plug it in, and you're going to get negative 1, 0. So this is not difficult. This is very simple. It's the same idea that we did all the way back in chapter 1. Now, let's go ahead and talk about continuity. Note that the vector at r negative 1 is equal to negative 1, 0. So r is continuous at the point t equals negative 1. So here was the limit. Here is the value of the function. They're both the same, and therefore it is continuous at t equals negative 1. So furthermore, let's talk about the component functions in their continuity. The function f is continuous for all real values of t. The function g, however, is continuous only for when t is greater than or equal to negative 1 because we're dealing with the square root function. So therefore, this function r of t is only continuous from negative 1 to infinity. In other words, it's not going to be continuous, at, I don't know, negative 3, for example, because if we put negative 3 in for t, that's not going to work. All right, so let's talk about the derivative. The definition of the derivative for a vector valued function parallels the definition of a real valued function, so this is really nice. For a vector valued function r of t, if we want to do the derivative of it, it's just the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. Similar to finding limits of vector valued functions, differentiation can be done by a component by component basis. This is important result is listed in the next theorem. Note that the derivative of a vector valued function R itself is a vector valued function. So if I have this vector valued function that's given by the following, then the derivative of the vector value function is simply the derivatives of each of the components. So let's find the derivative of our R vector valued function, R, and then let's go ahead and sketch it. So first of all, what is the derivative of t? Well, it's 1. What is the derivative of t squared plus 2? Well, it's 2t. So there's the derivative. Very simple. The position vector of R of t can be, we can write that in a parametric equation where x is equal to t and y is equal to t squared plus 2. And the corresponding rectangular equation will be y equals x squared plus 2, where t is equal to 1. So r of 1 is equal to 1, 3. R prime of 1 is 1, 2. So here's our graph. Here's our graph of r of t, the vector valued function. And if we were interested in the derivative when t is equal to 1, well, when t is equal to 1, we got the derivative is 1, 2. And so that tells us that this vector right here, 1, 2, that gives us the derivative. By the way, remember what we looked at last time. This vector here, this is a directed line segment that goes from, let me erase this a little bit, I'm getting too much on here. This is a directed line segment going from, it goes from 1, 3, and then it goes up 2 over 1, right? So over 1, up 2. So it goes over 1, up 2, so that's 1, 2. So here would be that same vector from the origin. So notice it's over 1 and up 2. All right, properties of derivative. If you're going to do the constant of a function, constant multiplier, you can just pull out the c and do the derivative. Sum and difference rule works. Notice that the product rule is just like the product rule for differentiation. So you got to do 1 d2 plus 2 d1. Now when we do the chain rule, it's the same thing. So if I'm doing the vector valued function and I'm plugging another function into it, notice that that function is not a vector valued function. I just do the same thing. Derivative of the outside, leave the inside alone, times the derivative of the inside. All right, integration of vector valued functions. Guys, it's basically the same thing. The antiderivative of a vector valued function is a family of vector valued functions, so you're just basically going to do C1 and C2. So for example, if I want to find the integral of a vector valued function of r of t dt, it is simply going to be the antiderivative of f of t plus c1, comma, the antiderivative of g of t plus c2. And so that would be simply the antiderivative of r of t plus c. So let's see an example of that. Let's go ahead and integrate this, and then let's go and do FTC for that. So let's look at A. What is the antiderivative of t? Well, that's t squared over 2. What is the antiderivative of 3? Well, that's 3t, and then plus c. Done. Now let's do FTC. We're going to break it into its component parts. The antiderivative of t to the 1/3 is going to be t to the 4/3 times 3/4. We're going to evaluate that from 1 to 0. And the antiderivative of the e to the negative t is negative e to the negative t. We're going to evaluate that from 0 to 1. So you're going to get 3/4, comma 1 minus 1 over e. Guys, this is not difficult. It's actually very simple. Last but not least, I want to talk a little bit about particle motion. So guys, velocity is the derivative of r of t. Acceleration is the second derivative. And of course, speed is the absolute value, or if you want, the magnitude of the velocity. So if we are given that r of t is this, let's go ahead and find the velocity, the speed, and the acceleration. So velocity is just the derivative. So the derivative would be cosine t over 2 minus sine t over 2. The magnitude, or what we would call the speed, the magnitude of the velocity is the speed. So we're just going to do the square root of, and then we've got to square those component vectors, which, by the way, that is equal to 1. So that is equal to 1. And then last but not least, the acceleration, which is the second derivative. So we have to do the derivative of the derivative. We're going to get negative 1 half sine t over 2 minus 1 half cosine t over 2. And then you can probably figure out the rest of this. So we got displacement here and total distance. So the nice thing is these vectored value functions extend very nicely from what we already know from other topics. And that brings us to the end.